Well, thank you, Jimmy. Just the very first thing that always has to be said on a Zoom session like this is, can you hear me? Am I off mute?
You are
Awesome.
off mute. We can.
Okay, I see thumbs up from Alex. I hear him off mute. Awesome, thank you. Like he said, my name is Clair Sullivan, and I am speaking to you high in the mountains of Colorado. Good morning, good afternoon, good evening, wherever you might be speaking to it or dialing in from. Just thank you for coming and listening to this talk today. I'm going to get started by sharing my screen here, and I hope if you're not seeing my slides, then somebody let me know. Now, the kicker here is that just with my monitor set up right now, I cannot see the Q&A window. So I hope when I get to the end of the talk, I'll pop back over to the Q&A window so that we can, have some discussion based on what you see today. I usually like to do it more in real time, but there are reasons why that's a little challenging today for me, but yeah, so let's get started with the talk. I'm going to talk today about doing machine learning with network graphs and connected data, and why. Who cares? What might be a possible benefit of doing this? So today we're just going to start off with just an introduction about graphs. What are graphs? Why would we want to use them? How do I even know if I have a problem that would be benefited by working with graphs? Like I call that a graphy problem. And then how would we create a graph? A lot of times we have graphs and we just don't even realize it. And then supposing I do have this thing called a graph, what can I do with it that, might benefit some problem that we might have in machine learning or data science? And then let's actually do some ML with graphs. Okay, let's just get straight into it. Really bare bones basic stuff here. What is a graph? I mean, simply put, a graph is just stuff connected to other stuff, right? So I've got this idea of nodes, and those are those things in the circles that you see there. Sorry, that's my pair programmer in the background there. Anyway, so these nodes, they could be anything. They could be people. They could be routers on the internet. They could be parts of maps and wayfinding. And then the nodes are connected to other nodes through these lines called relationships. So relationships, I mean, it kind of sounds straightforward. A relationship defines what that connection is between my two entities or my two nodes here. So graphs are everywhere, though, if you really think about it. We have some obvious examples like social media, but then there's some less obvious examples like search, for instance. If you look at things like the Google Knowledge Graph, I mean, the word graph in there should imply that we're dealing with a graph, but really that's just how is one bit of information related to another bit of information. So when we talk about search algorithms, a lot of times they're graph-based. And then question answering systems, knowledge graphs, things like Siri or ALEXA, which I can't actually say out loud because then she'll start giving my talk for me. So yeah, let's talk about some graph terminology before we really get into the ML weeds here. So this is probably a review for some, maybe new for others. It's all good. We have this idea of a graph with node and relationships, but we can have this thing called a directed graph, an undirected graph, a weighted graph. What I'm showing here is what we call an undirected graph. So I have relationships between two nodes. And this would be like Facebook, for instance. If I have here's me and here's my friend, and we're friended with each other, and we have to both be friended with each other. There's no idea of I'm friended with them, but they're not friended with me. Okay, so that's an undirected graph versus, say, Twitter, which would be a directed graph. So Twitter, I follow this person, but this person does not have to follow me back. Okay, so that's you see how we added arrows to those relationships there. And then there's this concept of a weighted graph. And what weights do is they give you an idea of, say, quantifying the relationship. Maybe it's the strength of the relationship. So for example, if you look at the blue node that's in the center and the blue node roughly at the 1 o'clock position, you see that there's a weight of 10. Okay, so maybe that's how many times two people are communicating with each other on Facebook. Or, an opposite example would be like in map wayfinding. Those are two cities, they're connected through a road, and that road is 10 kilometers long. Okay, so that's just kind of some basic graph terminology we have there. We also have this idea of what we call the adjacency matrix, because people say, okay, well, I've drawn circles and arrows between them, but how am I going to turn that into math that I can, actually run machine learning on? Well, it all comes back to the idea that you can convert a graph into a matrix. We call it the adjacency matrix, and really all it is, it's a square matrix, n by n, where n is the number of nodes, and all we're saying in this matrix is whether or not there is a relationship between two nodes. For example, here we have a directed graph, and if I look at my central node A, my central node A has outgoing relationships with several nodes. For example, A has a relationship with node C. So if I look across row A and I get to column C, I see that there's a 1 there, indicating that directed relationship. If I were to go down the column of A, I see everything that points into A. Okay, we call those things going out. We call that out degree. The arrows coming in, we call in degree. And so you can imagine if this was a directed matrix, this would actually, a directed graph, this would be a symmetric matrix. But the whole idea here that I just want you to take away is, yeah, we can turn a graph into a matrix and we can do math on matrices, which is good because that means we can do fun data science problems. Okay, but why? I mean, we're adding this level of complexity here. Do we really need it? Do we really care? Is this really going to get me anything more than what my traditional pipelines can get me? Well, let's talk about that a bit. This here is a screen grab from Kaggle, and it's a churn prediction problem that they had going on. And, this is our typical columnar data format. We've got columns that are customer ID and credit score and geography and and we're trying to predict based on these features whether or not a given user or customer is going to churn. Okay, pretty common problem. And that's all well and good. We could come up with some sort of machine learning model based on this and get whatever accuracy we get. That's great. But let's consider, let's say we're looking at customers here and whether they're going to churn. Maybe this is a social network. Am I looking at what's the probability that a given user is going to churn on my social media platform? Well, that's actually a much more interesting problem because it's not just a matter of whether that individual churns, but that individual's churning could be actually determined based on the others around them who churn. So for instance, I've created this cute little social network here for Barack Obama. Okay, and in this graph, I see that he's got a relationship with Joe Biden and Nancy Pelosi and Michelle Obama, and tangentially to other people here, Mitch McConnell being on there, Sasha and Malia. Okay, the point here though, let's say we're trying to calculate the probability of Barack Obama churning off of our platform. Okay, and we've got our columnar data. We know, whatever age and gender and location and stuff like that, just like was on that previous slide. But when we did our calculation on the previous slide, on this slide here, what we did was we made this assumption, and it's a very fundamental assumption in machine learning. Okay, and what that fundamental assumption says is that all of my data points are independent of each other. And in some cases, that's a perfectly great assumption. Okay, but let's break it now. Okay, this is a new paradigm for ML. We don't like to break this assumption, but we're going to do it. Okay, so what I'm going to say here, I'm going to throw out the concept here that maybe if Michelle Obama were to churn, then Barack Obama's probability of churning has gone up. Okay, so what I did there was I said, okay, understanding that there is a relationship between two different rows in that data frame that I showed you, that just broke our traditional machine learning model assumption, but might have given us a more accurate model. Let me give you an example of when that was actually true. Everybody's like, why do you have a picture of a mailbox on your slides? Okay, true story. Several years ago, I built this house here in the mountains. Okay, I didn't actually build it. I hired somebody to build it, but let's go with it. So I built this house, and I have a big box store, hardware store up the street. And so I was going and buying lots of stuff from them. So they see, oh, okay, well, Claire just bought a whole bunch of wood and a whole bunch of nails. I think Claire might be building a house. Okay, and then a little while later, we see Claire buys things like wiring and drywall. Okay, Claire's getting a little further along down this house building process, and then there's siding and fixtures and things like this. Okay, so my local hardware store can then recommend to me things to buy that help in the purchase, the building of my house. Except at one point they did, and this is true, they did recommend, oh, okay, well, you're probably getting towards the end of this process. You might want to think about buying a mailbox. Now, I'd been buying pretty much everything else on this recommended list, whether they recommended it or not, but I didn't buy the mailbox. Why? Okay, well, here's an interesting thing. They said, okay, well, Claire follows this profile of people building houses, so we're going to recommend these things. But what they did not look at was the relationships that I have to all of my neighbors where I live here in the mountains. Okay, so for instance, my subdivision here. If they looked and saw Claire is geographically related to all of these other people who've built houses, oh, gee, none of them bought mailboxes. Okay, so why didn't Claire buy a mailbox and none of these other people? Well, it turns out we actually don't have mail service here. Okay, we have to use PO boxes where I live. So true story, this, I'm not going to name names, but this big hardware box store has an entire row of mailboxes in the storehouse that is just collecting dust because nobody up here has mail service. They did not develop a proper machine learning model based on the relationships of the different customers that they have. And I don't even want to know how much money that costs them by not considering the relationships between the data. So, okay, hopefully that's been able to motivate you that there might be something here. But how do you really know if you have a problem that might fit into this paradigm? How do you know if you have a graphy problem? You know, a lot of people will say, well, I've just got, you know, I've got all of my data in SQL. What's the problem here? You know, I'm going to go back to this churn prediction model here. You know, you have columnar data, you've got RDBMS formats for your data. That's all well and good, but how do you know if you really have a graphy problem? And here's a rule of thumb that I like to use, which is that if you have to do more than a couple joins in SQL, then you should suspect you have a graphy problem. Now, it may or may not behoove you to solve it as a graph, but what I will tell you, those of us who work with SQL a lot, we know that joins are slow, very slow. Okay, and not only are they slow, but frankly, writing them is hard. I mean, I'm just going to say it. It's annoying. You know, the queries get long. They get really long just to look at on the screen, not even counting how long they take to run. Whereas if you consider them in a graph format and you have a query language that is designed for querying things based on relationships, not based on rows, but based on relationships, you can have a faster solution, and it's also a much easier to write query. So let's look at we're going to play the Will It Graph game. You know, I don't know if you remember Will It Blend. If you're not familiar with Will It Blend, go look it up on YouTube later. It's a giant time suck. I'm just going to warn you right now, but Will It Graph. Okay, so Will It Graph, MNIST. This is the famous handwriting. We're going to try and identify what character, what numeral has been written here. Will it graph? Well, the answer is, if I look at MNIST, yes, it actually will. And that's because when we're talking about images, and I'm not talking about images of random noise here, but I'm talking about like images of real things. One pixel is related to the next pixel. I'm not going to have a pixel that is bright red and expect the very next pixel to be bright blue. Okay, there is some sort of continual relationship on a pixel by pixel basis, and that can be captured in a graph, as is shown here. Let's look at another one. Facial recognition. Will it graph? Well, probably you're going to figure out the trend here. The answer is yes, it will. There is a relationship between each of those geographic landmarks across my face, and that relationship can be represented as a graph. Drug discovery, of course it can graph. Okay, and I'm two different graphs here. First, on the left, I've got molecules, and molecules, I mean, they even look like graphs. They're a graph. On the right is looking at peer-reviewed journal articles around coronavirus. Of course, we're all just so excited to see another data set around coronavirus, but we can get into the weeds about what that data set actually is and how it's graphed. But yeah, drug discovery, absolutely, will graph. Natural language processing. This is actually one that I find really kind of fun to think about. Of course, it will graph because everything else of these examples do. But if you think about it, words in a sentence are just nodes, and they have relationships to other nodes. Like I'm showing here, I have verbs and they have relationships with nouns, and nouns have relationships with adjectives, and I can draw those as, you know, words that are connected through arrows to other words. So yeah, NLP, very fun graph problem. Here's one, body composition analysis. I had no idea this was a thing, but it is. You can look at like the dimensions associated like with your body composition, how long is a limb, or how wide is a portion of your body, and that actually graphs too. And so all kinds of things graph that we don't think of as graphs. But again, just come back into your head. More than a few SQL joins, start thinking that you might actually be able to solve this problem more efficiently as a graph. Okay, what do you need to do that though? Well, let's talk about it. First, we have this concept of nodes, right? We talked about those before. Nodes are unique things. It'd be nice if you have unique identifiers. It's nice if you have properties. You can throw those in there too. Don't have to, but just if you want. So we could have a list. We have a node list. Okay, and then nodes are related to other nodes somehow, and those are through relationships. Sometimes we call them edges. Okay, so we have a node list and we have an edge list. It's nice if you can specify what the edge is. You don't have to, but sometimes we can have graphs that are really very elaborate graphs that have multiple types of nodes and multiple types of relationships. And that can just really enrich your overall analysis when you have those. And then, of course, we talked about relationship weights before. If you got them, use them. Okay, so we've got nodes, we've got relationships, and then we need this thing called a graph model. We'll talk about that in a minute here. But think about when you have, your SQL tables connecting, I got this table that connects through this identifier to some other table. And then the last thing that we're going to need to do in order to answer all of this is a question that you want to think about is whether you want to do your graph analytics just on your local machine in memory kind of thing, or whether you've got a problem that should be going out to a graph database. What I'm going to show you today, I'm going to be demonstrating a graph database called Neo4j, but it can be, the problems that we're going to do today can be solved in any number of other ways. NetworkX is a very popular open source Python package for graph analytics. There's also a few different ways of doing this in Spark. There's tons of different graph packages out there. Your decision, though, on which one that you use will, of course, depend on, like the usual stuff, scalability, what infrastructure do you have available, things like that. So I will tell you that, for small graphs, NetworkX is great. When you start getting into like big graphs, by big graphs, what I mean, I'm talking, hundreds of millions of nodes and billions of relationships. Those are big graphs, okay? You're not going to be able to do that in memory. So you got to give some thought as to where you're going to do all of your compute. Okay, so let's just look really quick at node and edge lists. I'm going to be showing you a graph today based on Game of Thrones. You don't have to know Game of Thrones to understand what we're looking at here today, but just to give you an idea of what data is in the data set. All right, so in the upper left, we have our node list. And, don't worry about these first few columns of numbers. I've got a name of my node. In this case, I'm looking at nodes that are people. And so my node has a property of name. My node also has a property of title. In some places, those are populated. In some places, they are not. I have a column, which is the property of male, which means is this person a male or not. I have culture indicated in some places. The idea here, though, is that my nodes can have 0 to several properties, many, however many you could think of. And all of that gets represented in a node list. And then I have my relationship list, which is this thing at the bottom right here. And in this case, I have a few columns here. I have we're looking at battles in this case. And I have a battle called, for instance, the Battle of the Golden Tooth. Now, I've read the books, I've seen the shows. I have no idea what the Battle of the Golden Tooth is. Just go with it. But I have this battle. There was an attacker king and a defender king. It happened in a year. And so basically what I'm doing is I'm setting up relationships between my attackers and my defenders and things like here. If you look at the bottom of this slide, there is a repo that has all of this stuff. And so you can go and, peruse through all of the node and edge lists that are available within this graph. Okay, let's look at the graph model here. And this is kind of hard to read. I apologize based on font size, but basically what we're looking at, we have different node types here. Okay, so for instance, the red node that you see kind of in the, call it the 10 o'clock position from that central cyan colored node. That red one is house. The central one is person. Okay, so I've got I have node types house, I have node types person, all the way over at the 3 o'clock position in navy blue is book. Which book did it happen in? I have, if you go straight up from book, the orange one is king, the yellow one is knight. Okay, so I have nodes here, and an individual entity can have multiple node types. For instance, a person could be a king, could be a knight. Okay, no spoilers, but the one that's kind of like at the 6:30 position that's kind of magenta is dead. Okay, so a person could be dead. So I can represent my data here in many different ways. And it's important to sit and think about your data as we do this. And people ask, what's the best way to do this? And literally it is a whiteboard. Sit there and talk about, well, what do we care about here? Well, I care about people. Okay. I care about what houses they belong to, maybe. I care about what battles they were involved in. How do they relate to each other? You're just literally drawing like circles and arrows on the whiteboard. It really is one of the most efficient ways to get this process done. But at the end of the day, what you see here is the data model that we have for all 5 of the existing Game of Thrones books. If he ever releases any more books, I have so many talks I have to update. So, but I'm willing to sacrifice for getting the books. Anyway, we have this model here. Let's actually look at what it looks like. Okay, this is just, it looks like a hairball on a screen. But in this graph, there's over 2,000 nodes and relationships. It's a pretty robust graph. I'll show you later how you can create this graph for yourself very simply. But just, you're looking at many, many, many different relationship types, node types, and it's all available. You can just pre-populate a database for yourself really quickly. I'll show you how in a minute. Okay, I've got a graph. Great. What can I do with it? Well, lots of things. First, the common graph analytics things that people are asked to calculate: degree centrality, betweenness centrality, PageRank. These are all centrality algorithms, and they measure node importance. How important is a particular node within the overall graph? Degree centrality, what it looks at is how many arrows are coming into or out of a node. So for instance, in that graph that you see right there, that central node A has all of the arrows coming into and out of it. It's got the highest degree centrality. Now I could say, what's got the highest in degree centrality? So that's considering only the arrows coming into the nodes. What's the out degree centrality? Those are the ones going out. Betweenness centrality, that's a fun one. It's not going to be well represented by this figure, but just take a step back. Let's say that you are in your office and you want to have a meeting with the big boss person. How are you going to get to the big boss person? Well, maybe the way to the big boss person is through their deputy boss person. Okay. Still might not be the best way, because that person's also very busy too. Who's going to be the person who is most likely to get me most efficiently to that big boss person to get a meeting? I could go around to all of my friends, but the more efficient way would be go to the administrative assistant of the big boss person. They may not have the highest degree, but they're the ones who are that connecting point to the important people within the graph. So that's betweenness centrality. And then there's PageRank, very famous, made famous by Larry Page and friends. It was the original backbone of Google. And what we're looking at with PageRank here is, how can I identify the importance of a node based on what links to it? And so Google did this for the entire internet, and they looked at which web pages linked to which other web pages. So, just a little cute example here. We've got each of these circles would be a web page. These nodes are web pages, and then you can see their links going out of them. And I've got the size of the node represents the page rank. So the larger the page rank, the larger the node. So the green nodes are little because they link out to stuff, but nothing links into them. So nobody really cares about those. And then there's that blue node. A lot of green nodes link into it. It links out to a whole bunch of things. But then there's that yellow node. And that yellow node is like everybody's linking into that. That is an important node. That's got the highest page rank. But then look at that red node on the top. It's got a pretty big page rank. Why? It doesn't have a very high in degree or out degree. But notice that the thing with the highest page rank links to it. That means that it's a pretty important node in that graph. So page rank is a mathematical way of quantifying the importance within the graph, just based on linkages. Okay, I mentioned pathfinding before. So this is actually, we talk about shortest path calculations, really great for a graph problem. So for instance, I'm showing I live in Breckenridge, Colorado, how to get to the airport. And this is just throwing it into Google Maps. Okay, y'all have done this a million times. I can see here, though, that Google did not route me through what is the geographically fastest way. Why? And that's that thing over by Denver that I've put in a box. It knew that I-70 was closed. That's usually the best way. So Google is able to dynamically calculate the shortest path weighted. It uses weights. So it says how long does it take to go this segment to that other segment. So it's using a weighted graph to optimize my path to the airport. Okay, now in reality, I was doing this, I created this little thing midweek sometime, but on the weekends, that's actually not the fastest path at all. The fastest path, if you look kind of straight south of Breckenridge, Alma, and Fairplay, that's actually the fastest path on the weekends because the traffic coming up here to ski on the weekends is huge. So fastest path, shortest path, these are all weighted graph calculations. Okay, another thing that we can do with graphs, community detection. Wonderful application. There's a whole bunch of different ways to do it. They involve math. I'm not going to go into the math, but just know that when you actually have assembled a graph, if you do it right and you model your graph properly, you can detect communities in your graph. You can detect sub-communities within communities, all very popular. The Louvain modularity one, that's probably the most popular of all of them. Connected components is probably the easiest of all of them. So if you're interested, I'll show you some references where you can read about how those things work at the end. Okay, and then this is going to kind of segue us into our machine learning bit here, graph embeddings. So of course, when we think about machine learning, everything is a vector, everything's an embedding, and we use, we turn things into numbers, and we use those numbers to, run math on and get probabilities out the other end. And that's going to be true with graphs too. We have ways of converting graphs into numbers via graph embeddings. There are several different ways to do it. Some of them are transductive, some of them are inductive. Transductive means that I have my entire graph, I train it, and I get the embeddings out. But that if I get a new data point in, I get a new node in my graph, I have to retrain it all. Inductive, I can do that on the fly. Now, of course, there's no such thing as a free lunch. If I use an inductive embedding model, then I have to expect that I'm going to need more compute to calculate those embeddings. There's things based on matrix factorizations, random walks, neural networks. It's a really hot area of research right now, but there are some that have kind of become standards. We'll talk about one of those in a minute here. But I call out FastRP and Node2Vec. We're going to talk about Word2Vec here in a minute. So just keep Node2Vec in the back of your mind. The similarity of the algorithm name. It's a hint of what's coming. Okay, so I've got these graph embeddings. Then what can I do with graph embeddings? Well, the answer is pretty much anything I want. Anything that I can do with a traditional ML approach on a normal embedding, a normal vector, I can do on a graph embedding. It's just a list of numbers, right? Doesn't matter where that list came from. So I could do things like node similarity with any of our usual similarity calculations like cosine similarity. I could do clustering. I could do classification, anything, really. Okay, so let's actually talk a little bit now about doing ML on a graph. Okay, grab a quick swig here. Okay, so traditional machine learning. Let's talk about, NLP. And we use word vectors. And so I'm just showing, this is a simple example based off of Word2Vec. And it's looking at a skipgram approach of how you'd work through a sentence and create vectors for each of the words or the sentences or the whole document, depending on, what your interests are. And so I'm showing here, we've got this sentence, gave a research talk in Boston. Okay, and so we're taking those words, we're turning them into numbers, and we're mapping it into in an n-dimensional vector space. Okay, so if I were to take my n-dimensional space, reduce it down to 2 dimensions, then I get the graph, the figure that I have on the right here. And so I've got some word embeddings here now. Okay, and then I have this other sentence, and we're looking at the similarities between the words in these two sentences. So my other sentence had a science lecture in Seattle. Okay, using those embeddings, I can see similarities between different words. For example, I can see that research and science appear very close together in this plot. Boston and Seattle appear close together, but science and lecture do not. Okay, and that's because semantically speaking, they are different words, and the machine learning, the NLP, knows that. So when it creates those vectors, we know that vectors that are closer together are similar and further apart are different. Okay, same thing is going to work in a graph. Okay, so we're going to actually node to vec works in a similar way as word to vec. So node to vec and word to vec are similar. And FastRP is something I'm going to talk about a bit. The idea here, though, when we're trying to go from, how did I go from word to vec to node to vec? Well, in word to vec, like I said, we did a skip gram approach through our sentence, looking at, which words were, separated by one other word to which other words. Okay, that implies a sequence, though. A sentence is a sequence. It has an order that makes sense, but a graph doesn't have a sequence. A graph is just, nodes and relationships. And there's no concept of a sequence there. So when we talk about vectorizing a graph, what we're really thinking about is skipping around the graph. We're going to do some sort of random walk around the graph. And that random walk, did I randomly hit this node or not? Yes, no. Okay. So think about one hot encoding. Did I hit this other node? No. Okay, so I'll put a 0 there. Did I hit this node? Yes. Okay. So I have walks of a given length, just as I would have windows of a given width within word to vec. And again, we just wind up with a list of floats, same as you get with any NLP algorithm, list of floats. Straightforward. Okay, so now I have a list of floats. I have an embedding. It happens to be based on graphs, not words. It's all good. What can I do with it? Well, I can do classification. Binary, multi-class, multi-label, doesn't matter. If it's an ML problem, I can do it. I can do regression, I can do clustering, dimensionality reduction, similarity. Okay, all of those are traditional ML things, but I can also do things that we couldn't do with traditional machine learning. For example, link prediction. What is the probability? I have a node and I have another node. What is the probability that those two nodes are actually connected, even if I don't have data that says they are? Okay, so I used that Barack and Michelle Obama social network case. What if I didn't have that connection? Barack Obama was just getting onto social media. I want to recommend people for Barack Obama to follow. Okay, who am I going to recommend? Well, I'm going to recommend the people with the highest probability that he's going to have a connection with already. Okay, and that might be based on the fact that, well, I saw that Nancy Pelosi and Michelle Obama are connected, and so Barack Obama is connected. So maybe Barack and Michelle Obama should be connected. And if you're interested, it's actually a problem that I show in a workshop that I give sometime on knowledge graphs, that I actually do a knowledge graph example of creating a graph out of the text for Barack Obama's Wikipedia entry. And Michelle Obama appears nowhere in there. So just by sheer luck of when I started creating that workshop, we had to predict the probability. Well, shoot, Michelle Obama, what's the probability that she's going to be connected to Barack Obama? So real world problem. Also, subgraph level structural similarity. We don't have to restrict our models just to individual data points. What's the probability that this group over here has a particular characteristic? Maybe I'm looking at the people in this session today, and we can talk about the communities that are forming here. We've got Kubeflow people, we've got MLOps people, we've probably got some people on the line who are data scientists. What are the probability that the people who are not Kubeflow but data scientists are actually related to the MLOps folks? So we could talk about that at a subgraph level, which is really useful, by the way, in like big drug pharma discovery. What's the probability that this portion of the molecule could actually treat this portion of a disease? Okay, just really quick, I'm going to just show some results that I got doing machine learning on a graph. And it's just a really simple graph here. I'm going to use FastRP. I mentioned FastRP and node to vec as being two very common embedding algorithms. I'm I'm not going to go into the math right now. Suffice it to say, the whole goal here is we're doing these random walks. We're establishing a high dimensional space, which we're attempting to look at having a limited number of dimensions represent the overall dimensions. It's just the same dimensionality reduction stuff that we deal with every other ML technique. The math is there's an article link that I wrote up about how that math all works. You can go read it if you're interested. Or if you're searching for the cure for insomnia, it's great too. Okay, let's talk about a real graph. So there is a graph called the CORA Dataset, and it's kind of like the MNIST for graphs. It's looking at scientific publications in data science. There are 2,708 entries within this data set that belong to one of 7 classes. There is some pretty significant class imbalance, but they fall in the areas of like deep learning and generative models and statistical models and stuff like this. 7 different classes, class imbalance, and what it's looking at is the citation relationships between each of the publications. So they took each paper and said, okay, what other papers does this paper cite? Okay, the data set also comes with the abstracts one hot encoded into a vocabulary. Okay, so they took the abstracts, they set a vocabulary of 1,433 words to which they one hot encoded. I will tell you that they have not provided the actual vocabulary. So when you download the data set, you're only going to get ones and zeros. I can't tell you what words they correspond to. So there's no way for me to tune the NLP on it. The vectors that you got are the vectors you got. Okay, so our graph model looks as what we see here. Very simple. Paper cites another paper. That's it. My paper nodes can have 3 possible properties: an ID, which is an integer. They have a subject, which is that class, so was it generative learning or probabilistic models? And then they have features, which those are those one hot encoded vocab words. Okay, so basically what I did was I just created a really basic model, and I'm not trying to create an optimal model here. I just wanted to have a very basic identical model, and I was going to use the NLP vectors, and I was going to compare it to the graph vectors, and that's it. So just a real basic support vector classifier, no hyperparameter tuning anywhere. The only caveat here, like I said, was that I did not get to tune the vocabulary. That's just data that they provide. Both models were given the same task, which was multi-class classification of an imbalanced data set. So let's look at the results that we got when we did it. So just throwing it bare bones, support vector classifier built into scikit-learn. Here's what we got. Okay, so this is using the word vectors here. Okay, so we got a mean accuracy of, about 73%. Okay, so we can see our confusion matrix here. Looking along the diagonal of that matrix, we can see that the numbers are kind of all over the place. I have a high of, 79%, and I have a low of 54%, which that ain't great, right? So what, it's not bad. I mean, it really isn't 73% just for a complete bare bones classifier. And, like I said, I don't have the opportunity to optimize any of the NLP on it. And I want to compare apples to apples here. So I'm really not going to mess around with the hyperparameters of the support vector classifier. Now, same thing. We're going to do it with the graph embeddings. Now, I will tell you that what I did, like I said, the word vectors were 1,400 dimensional vectors. The graph vectors that I use here, these are 10 dimensions. Okay, I literally told FastRP, give me a 10-dimensional vector output. Okay, and here's what we got. Got 85% accuracy with a 10-dimensional vector. Not only that, but look at the diagonal on that confusion matrix. Okay, the lowest value I get there is a 76%, and I go as high as a 93%. Okay, so if I just flip back and forth here, you can see that my confusion matrix has improved a lot. And obviously my accuracy has as well. Okay, furthermore, think about what just happened with your data storage requirements. I went from a 1,400 dimensional vector to a 10-dimensional vector. Okay, that's huge. That's really huge if you think about this, especially if we start getting into really big data. This isn't really big data. This is 2,700, entries in our data. I will tell you, I'm not going to go into it now, but I did spend a little bit of time tinkering around with the optimization of the hyperparameters for the embeddings, not the ML algorithm itself, just the embeddings. And I got that accuracy up to about 90%. And it's all because what we looked at was the relationships between the papers themselves. Papers within one class are going to cite papers within that same class. Okay, so just using the relationships, nothing more. That did not include the word vectors in it. It was just the relationships. And look what happened to the accuracy. Okay. Coming up on the end of the talk here, just wanted to throw out some really helpful references. First is this book, really great book. It's for free. You can go Google for it, Graph Algorithms, Practical Examples in Apache Spark and Neo4j, written by a couple friends of mine. Great book. It walks you through not only the math for how all of these graph algorithms work, but also, shows you the implementation in 2 different platforms so you can get a feel for how you would code that up in the real world. The bullet list there, the first bullet, I put out a weekly video called Bite-Sized Neo4j for Data Scientists. Every week on Fridays, it comes out, it's like 5 minutes or less, just, really quick. Let's just quickly look at how to do a different problem. We're around 20 videos at this point. This is a great time to be getting into the series though, because I'm going to be going completely back to basics starting tomorrow. Fingers crossed I can actually get this video done this week. But check it out. All kinds of stuff there. I also blog a lot about graph stuff, and you can find me on Medium there. I mentioned that I would show you how you could create a free database instance and have it pre-populated. You see here, there's this free Neo4j sandbox instance. And what this is just a free cloud thing. You go, you spin it up, you tell it you want the graph data science library. Okay, this is this thing in Neo4j that does all of these calculations for us, including calculating the embeddings. That particular sandbox, there's several sandboxes available there, but that particular sandbox has the Game of Thrones graph pre-populated in it. But there's all kinds of other pre-populated things and blank sandboxes that you can play with there as well, just to get a feel for how it works. And then lastly is a link to the Graph Data Science Library information, which shows you what all is available in Neo4j for doing this. Like I said, Spark has their own things, NetworkX has their own things. There's all kinds of other ways of doing this out there. So with that, I just want to say thank you. This is my Twitter handle. If I don't get a chance to answer your question today, please reach out to me there on Twitter. I am now going to stop share.